Hello, everybody. Welcome to Earth Science. So we're going to get at how to do this lab here because you were absent for it, and we'll get you all caught up here. The premise has to do with this line that you can kind of see here in the Google image, or in the Google Earth. So let's do a little backstory. First, a gentleman said, hey, this part of Africa kind of looks like it fits in this little notch of Africa if I played like puzzle pieces with them. And so that's kind of interesting. And he went and he found rock on both sides, and he found fossils on both sides, and he found glacial evidence from a really old glaciation. And lo and behold, everything matched. And he kind of said, hey, I think that these were together. And I proposed this idea called continental drift, where at some point in Earth's history, they broke apart, and South America since then has been boogieing across the ocean. And people were like, well, I see what you're saying, but you're telling me that a whole entire continent is moving across the ocean? How's that happen? And he didn't really have a good idea on how. And before anybody did figure out how, he passed away. So he never got to see his ideas like really come to fruition the way it did later on with full plate tectonic theory. Because once we started scanning the ocean floor, this is before Wegener. Before Wegener, we just thought it was kind of plain like a big bathtub down there. Post his passing away, we found out there's all kinds of cool stuff happening in the bottom of the ocean. And maybe the coolest is this mid-ocean ridge, this like mountain range in the middle of the oceans. So subsequent scientists working off of ideas that had evolved and been proposed, honed the theory, got it a little bit tighter, and said, hey, I think at this mid-ocean ridge, this is where the action is. This is where the spreading is happening. And it's the actual sea floor that's moving across, and that's just shoving Africa with it that way, and just shoving South America with it that way. It's not South America on its own going moving across the ocean. It's the ocean floor itself spreading open. Now, there's a lot that went into it, and we can't do every detail, right? But one of the things that is part of it, a big part of it, is that Earth has this magnetic field around it, right? If you've ever used a cheapo compass, I had one sitting here. If you've ever used a regular compass, that little tiny piece of metal detects Earth's magnetic field, which happens, which gets induced all the way down. Let's do a new tab here. All the way down in Earth's outer core. It's important for us to remember for other lessons that this outer core is a liquid. Wherever it is, page 10. This outer core right here is a liquid. In that, all of the churning of that iron and nickel induces the Earth's magnetic field. So you grab a cheapo compass that points north, it just works, right? What we've noticed in the rock record, pre-human history, is that what we consider the North Pole and what we consider the South Pole have flipped and flopped and flipped and flopped throughout time. There's no regular pattern to it. It doesn't happen like every X number of years. Sometimes they go whipping back and forth pretty quick. Sometimes it's very stable for a long period of time. There is, we're not quite sure what it looks like when it happens. Does it just turn off one day and turn back on the other day, or is it slowly fade and slowly pick back up? There's a lot of questions out there, but one thing we can definitely say is that on the ocean floor, there's these patterns that emerge. Now, we're not going to get into exactly what these patterns all mean. All we're going to say is that, hey, scientists have equipment, and if you want to go deeper on this, I'll talk all day about this. Scientists have equipment to detect the strength and orientation of Earth's magnetic field remotely. You can drag a boat with this equipment and the right training with this behind it. We'll drive the boat, drag the equipment, and detect what's going on the ocean floor. So we are going to like simplify this. There's a lot going on here. This could be a very difficult lab. We're going to make it a very easy one. You're going to need 3 colors. So the first one, I'm going purple. You do you. What I want to do is a line right on that dotted line. All right. That's going to be what we're going to label the ridge. Now let's make it purple so it matches. All right, that's the mid-ocean ridge, part of the mid-ocean ridge system. If I go to Google Earth again, that's this thing. People always say it looks like the seams of a baseball. They wind all over the planet, and everywhere that this is happening, the crust is spreading away from the ridge. The next lab after this one, which some of you may have already done, deals with the East Pacific Ridge, this ridge over here. It doesn't quite show up quite as neatly. Spreading over there. The Atlantic one just shows up. No problem. Nice and easy. And on either side of that, it's spreading out. So let's make our lab look like that too. On either side of the ridge, the crust is spreading. Now, the way it works, if you remember these diagrams that we did all these cross sections. A lot of this relies on us remembering where we've been, is that as soon as this cracks open, the little teensy tiniest little bit, fresh magma from down below comes up, squirts up, hits that ocean floor, solidifies into basalt, which means you've got brand new ocean crust. During the week that we're learning this, somewhere along this ridge, in multiple places all along this ridge, there's brand new ocean crust forming, which is pushing the Americas on this side further and further away from Europe and Africa on this side. So it's a good idea to make a note of that too, that right on the ridge, this is pretty much the fundamental key to this lab, is brand new rock. Okay, 0 million years old. Now we're going to pick two other colors to draw with. I'll do red. What am I going to do with the red? These numbers are, we're going to say somebody else did this work for us. They did the hard part. They identified certain patterns within these anomalies. All we're going to do is say, great, I'm going to connect the dots and make my life easy. Maybe easier to zoom in a little bit. We're going to connect with the first color, 1 to 1 to 1. And if you're a little wobbly like me, that's okay. Don't worry. To 1. That should run right along parallel to that. And then the same color, 1 prime, 1 prime. Oh, well, let's try that again. 1 prime, 1 prime, 1 prime, 1 prime. And the idea here is that those correlate with each other. This one and this one have spread about the same amount away from that ridge. Maybe one side's going a bit faster, but about the same from the ridge you go out. That would represent one of our magnetic anomalies. And if that's confusing, don't sweat it. It's just like the poles flip, flop. And one is what we call normal, just because this is when humans evolved and we exist. The other is what we call reverse. I'll go to green for my other color. And the other color is going to be the 2s. Try not to make them cross, but if they do, it's not the end of the world. 2 to 2 to 2 to 2. 2 prime, 2 prime, 2 prime, 2 prime. All right. That would be like reverse, right? Then it goes back again to normal. So I'll do that again with red. So it's going to like alternate. The 1s and the 3s are going to have the same color. And then it alternates back again. That's important. Don't do 4 different colors. It goes one color, then it switches back, then it switches back again. Red, green, red, green, red, green, or whatever 2 colors you chose. Mm-hmm. That's through the 4s and then through the 4 primes. There we go. That's it. All right. So the thing to notice is that as it spreads, it pops back and forth, right? As it spreads in either direction, it consistently gets older. So older crust going that way, older crust going that way, and it matches. The key term to this lab that's going to help you survive is, how would you say that this pattern, you can't see my hand, this pattern on this side compares to this pattern on this side? We're going to say, hopefully the terms pop into your head, we're going to say, and it's the most important word of this lab, that there's a symmetry. They are symmetrical. Put that right in there in that box in that ticket. That is the most important idea for this lab, is that there's a symmetry on either side of the ridge. The patterns on either side of the ridge are symmetrical. You get that down, you're going to be fine. This question deals with it. 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 That one does. That one does. It's all symmetry, 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 symmetry. That one does. All right. They're symmetrical on either side of the ridge. These magnetic anomalies. And again, even if you're like, what the heck, I don't know this magnetic anomaly thing. Loosely in your head somewhere, pole switch. Cool. But the big thing is the symmetrical pattern that has evolved, because it lets us know this is like the final, like, okay, this is it. There's plate tectonics. It lets us know that the mechanism, really, that new crust is formed here and it spreads out from that evenly. In the Atlantic Ocean, that's the deal. The new crust is right along that ridge somewhere. Again, today, some of that's going to form, no matter what day you watch this video. As you go out from it, it gets older and older and older, symmetrically. And right out here towards the edge, the continental margins here, it's about 200 million years old. So for about 200 million years, this Atlantic Ocean is getting bigger and bigger and bigger and bigger, but the crust grows out symmetrically. And just play that in your head. Play this like in reverse. If you rewound it, these two would come back together, right? For 200 million years, they've been spreading, 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 spreading. The Atlantic Ocean is getting bigger, 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 bigger. Slowly, but bigger. All right, so your jobs, bunch of regions questions that deal with symmetry, right? But first, there's nothing in this box that screwed people up. I should have colored that in. You're going to measure between the mid-ocean ridge and peak 4 a distance in kilometers. Then you're going to convert that to centimeters, and then we're going to get a rate of how fast that plate is moving in centimeters per year. And then this question will deal with that rate, saying, okay, if it's going that fast, how far has it gone since 1966? You know, which is like, you got the rate. If I'm driving 60 miles an hour, how far can I go in X amount of time? You know what I mean? It's just multiply it times that to figure it out. How do we get this distance? Well, you got this scale right here, and you can actually use Cami. I saw somebody do this, and it's like, it's brilliant. So if we had to go from the ridge to 4, it's about yay far. Then you can grab this tool, and you can come on down to your thing, and you can say it's about that far. That's it. That'll do it. I'm not going to actually do it on the screen. I want you to do it. But again, that was a measurement from the ridge, my purple line, to the number 4. Then take that, come on down here, compare it to the scale. That's going to give you a distance. Convert that to centimeters. We practiced at the beginning of the year. It's a video at the end of the year. Let's just make this quick. To convert it to centimeters, all you're going to do is add 5 zeros. You don't have to write this, but do it. It's going to be a great big number. I mean, it's a lot. This covers a lot of centimeters, right? And then divide how many centimeters per year. That's your rate. And then multiply it times the number of years that have passed between now, 2024, and 1966. 50-something years. Figure it out. Sound good? You got it, everybody. Keep it up. Good luck. Let me know if you have any questions. So long for now.